So I'll go back to the slides for a few seconds, and then I'll jump back up. So we looked at PhotoMisa. They use a different, they call it quantum tree map. Their tree map needs to kind of have a squarish, because you need to put thumbnails of pictures in there. This used to be a good representation of the stock market. You kind of saw parts of it in the Fund Explorer, where you have healthcare and kind of see what the market is doing. For a while, it used to be my best. Actually, I don't think it exists anymore. So that link, if you follow it, I'm not sure if the company exists anymore even. Can't remember, but a few years back it stopped working. But you could get an idea of what the stock market was doing, what sector was getting hit the most. You can see here some companies being hit on this particular sector. Everything else looking pretty good. We looked at it actually, I think it was on a Monday, 2008, when the stock market dropped like 700 points. We looked at it. It was pretty red. So for a while it was the best. Why do I think it was the best? Because there aren't maybe one problem with tree maps is that you cannot show that many levels. Everything we looked at, we had 4 levels, including the root. So after about 3, if you take the root aside, which is just the entire thing, 3 or 4, you kind of start to lose. You're not seeing the structure anymore. So I think if there is a drawback to tree maps, that may be it. And this one was just one that was using 2 or 3 levels. You could see the stock market, sector, and then individual companies. Now, that being said, when you go to Tableau and Tableau offers you a tree map, what I've seen in the past, maybe they've changed with the new release, but what I've seen in the past is their tree map has really only one level. They have the root is everything, and inside they just put one level. And I don't think that's necessarily a best. That's not why tree maps exist, to just have one show a tree that has level 0 and level 1 in it. So unless you find more levels, then it's not that useful. I mean, take that with a grain of salt from Tableau. One of the presentations that we had earlier in the semester had one of those, and actually for that particular data set, it was that what the advantage was of that representation was that one of the nodes was about as half as the sum of all the other ones. But if that's not the case, if your nodes are more or less the same, then a bar chart is going to be a lot better, because that's all, you know, a one-level tree map, all it does, it compares. It basically does what a bar chart does. It puts all of them together. You can compare their values, and you'll be a lot more precise in estimation with a bar chart than with a tree map. For a data set that has most things regular. So I looked at some other combination. People try to make them in 3D. So what this does is just uses computer graphics and 3D. So that used to be called Sequoia View. I think I have the program somewhere. And by the way, if you're running out of space on your hard drive, there aren't that many good applications to tell you where you have a lot of things that can get rid of. So a tree map like that tells you each individual's file structure. Because you may think it's the images, but may not be. Maybe your image, when you look at it, is just 10% of your hard drive. And if you to go there and try and get rid of some images may not give you. And actually, maybe you run into this more with a mobile device, because they're even more limited on space. So the next thing, Voronoi tree maps. Notice the irregular shape. They kind of take tree maps to me, I think they take it to the next level. It looks a little bit, especially the bottom one, Looks a little bit like chicken feet. The skin on the, I'm not sure if you've seen that, but looks a little bit like that. The advantage to me, so first of all, it's an irregular shape. You can have any shape you want. Notice that even inside one area, they don't really have the same shape. They can, it's not rectangles anymore, so it's kind of moving away from rectangles. But look at how many levels can you see inside? So for example here, obviously that's level 1 child. This is a level 2 child. This is a level 3. And if you look closely, you can probably see nodes inside of it. So I think you can go to 4 or 5 on this. It's a little bit better at showing different, the structure of a deeper tree structure. It's not, again, noding diagram, you can show a lot more because you can just put them one after the other, one after the other. But with these, they tend to be a little bit better to me. I can see more levels. Compare this to, actually I have the next. So compare something like this with something like this. Can you really see inside the tree structure? And of course they chose slice and dice, which is even worse, which makes it worse. But it's a comparison. So I'm going to play the video. I just don't want to switch back and forth too much. So I'm going to play the video for Voronoi tree maps a little bit later after we move on to the next topic. But keep that in mind. They have two ways of doing the tree maps. They kind of have them set up here, and that's a comparison. One caveat for this is that it takes a lot of iterations, and it's relatively slow in the sense that it may take a few seconds to update. So if you have a lot of nodes that you have to redraw, let's say something happened with your nodes, you filtered, and you have to redraw that, that takes a relatively long time. So it's not quite interactive for a regular sized tree. For, you know, if you have hundreds of nodes. Notice the NBA players, there were probably hundreds of players in NBA. That thing drew almost immediately, any change. For this, it may actually take a few seconds, 5, 6, 7, 8, 10 seconds. So it's not quite interactive, but it looks better and it has any kind of shape. So I will, now let me play the video right now, because we're moving into a completely different area. So the video is on under lectures. Okay, so starting in 3, 2, 1.
Centroidal Voronoi tessellations enable a non-regular uniform subdivision of a given area. By assigning a weight parameter to each generator point, it is possible to control the size of the subareas. This weight parameter is adjusted during the iterative computation to minimize the area size error of the tessellation. The result are non-regular subdivisions with an area size error below a chosen threshold. Here you can see the same procedure again. The difference is the usage of another distance function. In the foregoing animation, the AW distance function was used, that generated hyperbolic curves as boundaries. Now the PW distance function is used, that results in straight line edges. Complete tree map layouts can be obtained by performing this computation recursively. The achieved layouts satisfy the constraints for tree maps, optimize the aspect ratio of the subareas, and maintain the hierarchical structure of the data. Similarly to other tree map layout algorithms, enhancements like borders, adaptive edge sizes, cushions, or coloring may also be applied to Voronoi tree maps. Due to their recursive structure, Voronoi tree maps are not limited to layouts within rectangles, but rather enable subdivisions within circles, triangles, or other polygonal shapes. This allows for a more flexible adaptation of tree maps within a wider range of applications.
Okay, so now we're moving to the last section. We're still going to do space filling visualizations for trees. But now, instead of using a linear space, we're moving into a circular space. So that's called radial space filling. There's some papers that came up with it. One big difference between radial, I mean, obviously they're round. But one big difference is that, and I don't know why, but children are not inside their parents on this one. They kind of go, you can see the root is here. This is the root. And then these three children, they kind of go in concentric circles. And I don't know, I don't understand why they don't put them inside each other. Maybe there's a way, there's no way to look at the hierarchy that way. But for the most part, you can see that they're not put inside each other. They're just using a concentric track around their parent. So you can see, for example, these two green nodes are these two right here. They can still use the size, or maybe these two, I don't know, I can't tell. No, well, yeah, I can tell. They're the same. This subtree looks exactly like this one. So I won't be able, but it's those two nodes probably right there. The way that, again, the way that works, if you kind of draw a line, you can see that the green node has two children and they span the same angular distance between those two radii. So that's kind of how tree maps are constructed. And the rest, I have a video, and that's going to be the last part of this, that kind of shows what happens with when we have really thin edge nodes. So if a node is really small, then it becomes just one little line in there. And if it has more children, then you won't be able, the children actually are going to be forced to be even smaller little lines. So just one problem with radial space filling is that children can be really thin. And there is no other algorithm to do it. All you have to do, because everything is based on the angle, the span of the angle. So if the angle is really, really small, all you get is thin lines. You can kind of see many of these nodes here are very thin. Okay, so Sunburst, Georgia Tech coming. It's not the original radial space filling, but they look at the problem. How can we deal with the problem of really thin leaf nodes or even inside nodes? And they have three techniques. So one of them is the angular, and the video will kind of explain them, go detail on the outside, detail on the inside. And then that's pretty much it for trees, and it's pretty much it for chapter 3 in the book. So I'm going to show that video with Sunburst, and let's see if these 3 V's work. And then we'll be done with this set of slides. I think I have to just type it in. Okay, so sorry. So Sunburst. Starting in 3, 2, 1.
This video illustrates the Sunburst visualization system and 3 focus plus context techniques for examining small peripheral items in the display. Shown here is an example computer file and directory structure. The Sunburst interface has 3 main regions: the file display area on the left, the control panel in the upper right, and the color legend at the lower right. To begin, only the root directory or folder is shown, but the viewer can step deeper into the hierarchy via interface controls. Each successive level of files and directories is shown further from the center. White slices represent directories, and colored slices represent files. The angle swept out by a slice corresponds directly to the file or directory size. The color of a slice normally represents the file type. Alternatively, color can represent when a file was last modified. Here, the red files have been changed recently, while the dark blue files have not been modified in many years. The main problem with this type of visualization is the thin size of small peripheral files that makes it difficult to see and analyze them. Some examples are being pointed out here. When files are so thin, they become virtually indistinguishable. We have developed 3 focus plus context visualization and interaction techniques to address this problem. Shown first is the angular detail method. When a directory is selected by a double click, we shrink the entire structure, highlight the directory, move the structure to its opposite boundary, and expand the selected directory and its children. User interface controls allow the viewer to adjust radii and sweep angles of the focus directories and files. The technique uses smooth animation and contextual layout to help the viewer track interface transitions and examine the selected peripheral items. Note that in addition to selecting a focus item from the normal view, a user can select a new focus item from the shrunken overview as well as from the enhanced focus region of the visualization. This may assist the viewer to select items that are too small to be distinguishable in the overview. Here, we select a relatively interior focus directory in order to examine all its children in more detail. The second visualization and interaction technique is called detail outside. In this method, the entire structure is shrunk in the center of the display, and the selected directory is drawn in a new circular region surrounding this overview. The directory's children are displayed outside it as well. This technique provides a larger angular area for showing the focus items than the angular detail method does, but it lacks the geographical orientation between focus and overview that method exhibited. Like the angular detail method, new focus items can be selected from the overview or the focus regions as well. The third and final technique we have developed is called detail inside. In this method, the overview of the entire structure is pushed outward and the focus items are drawn inside it. This technique is conceptually similar to detail outside, but it does exhibit quite a different appearance. One advantage of this method is that small files in the overview are more distinguishable due to their distance from the center and corresponding longer circumference. Note again the use of smooth animated transitions between display states, as well as the contextual use of an overview of the entire structure in order to help viewers browse the file system without becoming disoriented. Finally, we'll select an extremely small peripheral directory to focus on and quickly illustrate the 3 techniques again in reverse order. Shown first is the detail inside method. Next is the detail outside method. Finally, the angular detail method is illustrated.
Okay, so you saw the radial space filling. Again, I'm not sure why they don't put them inside each other. Obviously, you've seen that you can look at 5 or 6 or even more levels of the tree. You can kind of go down pretty deep. So much better than the other one, than a regular space filling technique. And if you thought I really covered trees, you thought really wrong. Somebody did this website with all possible, well, at least the ones they could find, tree visualizations. So they're up to 307 right now. Okay, so here is looking dimensionality. So these are all 2D representations. 237 of them are. You can see them here. If you want them in 3D, there's 66 of those. Kind of quick overview. And here is hybrid, so it has a combination of 2D and 3D. There's only 4 of them, so not that many there. So let me go back to all. Representation, so explicit representation for the trees. You can kind of see all of them. They have very interesting looks. 131. Implicit representation of the trees. Again, you've seen some of these a few times now. And some sort of a hybrid representation. They're part of it, part of the plane, for example, here is implicit. Between the planes, it looks like it's explicit, they show. It almost feel, I don't know if explicit may be node link, but that's not true, probably. So as far as alignment, so these are using linear axes, they call them parallel. So these are all the techniques. Some of them look like pyramids. Some of them look like step tree. Radial, they look interesting. Some of them are round. And here is free representation. It's not quite sure what the axes are. So there's 29 of these as well. Okay, so the nice thing, if you go to this, click on it, you can actually see the paper they were published in and the year they were published. So that's a 2014 representation. Oh, these are pretty new. 2005 one right there. Okay, so that's the end of this set of slides and the end of chapter 3. Now we're moving into chapter 4 in the book.